Thank you so much, Thomas, for this invitation. We are very proud and very happy to be here. It's an honor for us. So now we are traveling to Valencia. You can see that it is in Spain, close to the Mediterranean coast. And we are going into Valencia city center. And in the city center, you have the old river bed, which you can be seen here. And now it has become a garden. And this old river bed is crossed by several bridges. One of them is the Puente de las Flores. In English would be the Bridge of the Flowers. And you can see a 3D view of the bridge here. It is quite a singular bridge because it has some palm trees and it also has some flowers on top that must be changed several times every year. So you can see here also a view from the bottom of the bridge. And this is quite a singular bottom or quite a singular underdeck structure. And the reason for that is that it is inspired by the timber ceilings that you can see in some historical buildings in the city of Valencia. So this is the reason for that. If we go a little bit on the details of the deck, you can see that it has some longitudinal beams, this like this and this one. Those are composite box girder. This is the steel part, and on top there is a concrete slab. These longitudinal girders, you can see them in blue, in purple, and in blue there. There are also some diagonal girders in green that can be seen also in the image. And finally, there is a girder on the abutments, which is a kind of eye girder structure. You can see the eye girder here. And these flowers, as I said before, they need to be changed every year. And the flowers come in pallets, as you can see on this image. And what happened is that they changed the flowers, they store the pallets under the bridge, and then somebody came at night and set the pallets on fire. So this picture was taken by the firefighters of Valencia. This is how the pallets remain after the fire. And I will show you also some images of the damage. So what you can see is that there was a spalling in some parts of the abutments up to almost 4 centimeters. There was also the diaphragm girder that experienced some important local buckling in the bottom flange. There were also some out-of-plane displacements in some of the girders. This is a closer look at the local buckling in the bottom flange of the diaphragm girders. Of course, the supports were completely burned. And also, we don't know if it was a consequence of the fire or maybe there were some problems with the construction, but we think that it was mainly the fire. There were also some cracks in the weldings. And in addition, you can see here the deck, and here you can see the abutment. The deck moved up several centimeters. So after the fire, logically, the bridge was closed. Also, the circulation for pedestrians and for bikes was maintained. And then some decisions had to be taken about what to do with the bridge. So we asked to the town hall if we could participate in the analysis and do some research. And then some tests were done, of course, with concrete. So some concrete specimens were taken and tested under compression. The sclerometer was also, all the weldings were checked to see if there were some invisible cracks or some damage that could not be seen in an evident way. Of course, also some 3D geometrical control with laser scanning and also with leveling instruments like traditional topographic survey. And then we started with our research project with 2 main goals. The first one was to learn from the incident because we had been doing research on bridge fire for over 10 years. And this was a big opportunity to have this full-scale test so close to the university. And of course, and very important also, to inform the decisions to be done on the bridge. And to do that, we did some fire modeling, some with FTS, some thermal modeling with SAFIR, and some structural modeling with SAFIR 2. And this is what Juan is going to explain next.
Okay, so as Nacho said, so based on the in situ forensic investigation, a performance-based CFE model was carried out to estimate the incident fire exposure to the structure. The fire size was taken from the in situ investigation, witness information, plus the results from the experimental test on piles of pallets carried out by the NIST. So in this case, 6 pallets were implemented, accounting for a peak heat release rate of a maximum of 34.7 megawatts. The control volume for the model was centered on the bridge first span, and it was really important that the correct resolution was chosen to basically capture the different smoke reservoirs created by the structural grid, as well as the gap due to the bridge expansion joint. So finally, the adiabatic surface temperatures values used to transfer the data from the fire model to the structural model were captured via more than 800 solid phase devices placed along all structural elements. So the CFD model went under detailed validation following in-situ investigation of the incident aftermath. So this mainly focused on the soot settlement and concrete spalling along the abutment concrete slab. So as we can see the figures, clear areas correspond to locations where flames impinge onto the structural elements, basically preventing settling of smoke soot. Conversely, the darker areas correspond to locations where soot settle due to the absence of flame impeachment. This qualitatively corresponds to the CFD model results. Additionally, the fire witness reported smoke spread along the bridge expansion joint during the fire incident. CFD model was successfully able to capture this phenomenon as well, corroborating witnesses' observations. Okay, so if we focus now on concrete spalling for the model validation, figure above, so adiabatic surface temperature for the abutment, the concrete slab at a peak heat release rate, as well as areas where superficial spalling was observed on site. So if I can use my laser point here, so in black here we can see the areas where spalling was observed in situ. The areas in red in the CFD model correspond to adiabatic surface temperatures between 750 degrees and 870 degrees, indicate or gives you an estimation where the spalling is expected to or was expected to occur. So if we look at the photos below, it can be observed that critical areas so labeled by the CFD results are generally related with those areas where the spalling was identified on site, basically within the central and the lateral areas along the abutment recess, closest surface slab to the fire. Within the data from the CFD model, heat transfer analysis was carried out for each structural member and concrete slab separately. So between 5 to 7 different frontier conditions were applied per section to capture the shadow effect. Due to the high number of sections and the fact that each in-file can be easily modified with a text editor, the data extraction for the CFD, the fire curve text file creation, and the in-file creation implementing its fire curve was automatically created via Python script using basically we were able to use a reduced number of base models helping with the model creation. The heat transfer analysis provided a detailed understanding of the temperature distribution within the structural members. While some elements experience significant temperatures increase, the majority of the elements maintain their structural integrity. However, local buckling was observed in steel girders suited to higher temperatures, the diaphragm girders here, closer to the abutment. Basically, we can see how the maximum temperatures were in excess to 700 degrees for the lower flange. Here in this slide, we can see the temperature distribution for the worst case abutment area, the point A1 here. Since the concrete cover of the steel rebars was 35 millimeters, the maximum temperature reached by the abutment reinforcement was less than 200 degrees. This temperature is much lower than the temperature at which the reinforcement started losing strength, indicating basically that the reinforcement did not suffer any loss of strength Now we can see the temperature distribution for the other areas, which are slightly less than the area highlighted before. This figure now shows the same temperature distribution for the concrete slab. We can see how similar temperatures which were achieved along the concrete slab. It was important because there was a question on whether the slab would have been affected by the fire. It needed to be reinstated, basically. So just with the heat transfer analysis, we were able to basically confirm that the concrete slab was maintaining its structural capacity. Now there are some graphs that didn't go into detail, but this apply to the other areas highlighted in this key figure. It's interesting to see how the maximum temperatures in the slab were achieved or were reached on the area S5 as opposed to the S1, what we would expect it, because this area occurs under ventilated conditions. So at the end of the day, this was the most effective area by the fire. With the information from the heat transfer analysis, a structural model was carried out for the effective bridge span. Fiber type beam elements were used for the beams, included the mechanical collaboration of the concrete slab and shell fitted elements for the concrete slab. The steel reinforcement is made laterally. No consideration was given for the shear connection damage or full connection, because a calculation was carried out on the temperature achieved, and it was concluded that the capacity reduction for the shear studs was less than 3%. For the boundary conditions on the abutment supports, a virtual spring on each support was implemented, only working in compression with high stiffness. On the other side, lateral and vertical constraints were imposed to the pier slab. Rigid connection, horizontal and vertical displacement was restricted along the submodel edge, and rotation was restrained along this edge on the Y global axis. It's important to say that this submodel was validated at ambient temperature against a full 3D model of the entire bridge, not done by SAFIR, but an external software. Due to the complexity of the grid and the model results from the mechanical analysis, it's important to know that we should be taken in a qualitative way. I'd like to thank Professor Jean-Marc and Thomas for their help and tips to achieve the numerical convergence when running these models. But a quick review to the axial load graph reveals how sections closer to the fire location were before the ambient temperature were either intense or under minimal compression. However, the fire and subsequent girders heating provoke a significant compression forces process in them. It's interesting to see the dynamic transformation of the diaphragm girder here in orange under high temperatures. Initially, this girder D1 experiences a rapid shift from nearly zero axial load to significant compression due to the constraints from the cooler adjacent structural elements. In fact, as compression in D1 increases, tension in L1 rises as well, peaking at 2.5 minutes. This is where the point A is located. Afterwards, as the other girders heat up and expand, this restraint is reduced, reducing the tension in the diagram, reducing the decompression in the diagram girder, and introducing compression or reducing the tension in elements like the longitudinal girders. Once the fire intensifies after around 6 minutes, the diaphragm girder heats up faster than the adjacent girders, leading again to additional compression. The graph on the right shows maximum vertical deflections for the models. These were recorded to be up to 90 millimeters in the worst case point, which is the mid of the slab S5 that we highlighted before. Results from this post-assessment investigation led to further investigate the potential impacts of design choices and the structural analysis methodologies on the fire consequences. To explore these aspects, parametric analysis was carried out to evaluate the risk response across the 5 scenarios outlined in the table below. The first scenario was the region analysis. The second one evaluated the response if I girder sections type would have been used instead of box girders. Third and fourth scenarios incorporated the effects of local instabilities using a modified effective stress in compression, which is coded in SAFIR for steel. And the last scenario modeled the diaphragm girder with shell elements, fiber type elements for the stuck connections. Results from the this parametric analysis for the heat transfer analysis reveals that the box girder design will act as a thermal insulator, shielding the not directly exposed wet from direct fire impeachment. Heat transfer within the internal cavity obviously occurs at a comparatively lower rate. On the other side, if a knife-shaped girder design would have been used for the bridge, we would have seen that higher temperature would have been concentrated along the bottom flanges. Member would have been exposed along the upper and lower surfaces simultaneously, facilitating a faster temperature propagation across the steel web. This slide shows the comparative results on the vertical displacement for the different scenario. This first one is changing the section type from the original model. Second one, different section type with implicit consideration of lock and buckling. The third graph is maintaining the same section type and different mechanical approach. I wouldn't go into more detail in causes of the time, but if I had to consider two main conclusions of extractions from the results, is that the I-girders show larger vertical displacement, obviously due to higher temperatures and thermal induced expansion. That the modified effective stress model accentuates these displacement differences between section types and reveals non-symmetric uplift and reduced peak deflections in general. This is a similar graph, both showing the axial load results. And again, there are two main conclusions that can be extracted, which is the I-shaped girders exhibit greater compression in the transversal girders and these ones, with higher tension in longitudinal and diaphragm girders. Two, that the modified stress changes the original model behavior, showing higher compression in box girders type of sections for transversal girders, as opposed to the higher compression in higher girders in I-girder scenarios where this modified stress is not considered. This slide will show displacement results from the 3D cell model of the diaphragm girder. It's to be noted that local instability in the model occurs at mid-span as opposed to close to the supports. This is because the model assumes a single fire curve along the entire length of the beam, fully fixed mechanical constraints as supports. Similar behavior to what is seen on site is expected to happen in the model with variable higher exposure along the girder length and more realistic mechanical constraint taking into account the rest of the model. However, it is clear how the full 3D shell model accurately capture local instabilities, improving the mechanical analysis for specific elements.
So now after all the modeling comes the time to take the decisions. So of course the bridge had to be repaired. So all the damage due to spalling, you can see that it was repaired using traditional methodologies. I will not explain more on that. Also the local buckling that you can see here, the idea was to cut more or less half of the I-girder and to replace with a new segment. This is what you can see here. They are putting the new segment and with some stiffeners too. Also, since the supports were completely burned, they had to be changed. So to do that, the deck had to be lifted. So what you can see here in blue are the hydraulic jacks to elevate, to raise the bridge. Since now new important point loads were appearing at the position of the jacks, these stiffeners had to be added, and all the process was monitored with LVDTs and strain sensors using fiber optics technology. And then in order to be sure that everything worked perfectly, finally a load test was done with tracks, and also the flexions as well as the strengths in the bridgework measure, and we're in a very good agreement. So basically, some things that we learn is that it is very important to preserve every evidence from the fire, because they are very helpful in order to reproduce the event. So this is important, and very often you arrive late and nothing is left. Also, we think that this kind of numerical modeling, in conjunction with load tests and with all the experiments, they enable to take very good decisions and very informed decisions. So the first approach that the owner had was to demolish the first span of the bridge. That would have been very expensive, and also the bridge would have had to be closed for a long time. On the contrary, by doing all these tests and all this numerical analysis, everything was optimized. And also, I think that it is very important to do more research on the comparative behavior of eye girders and box girders. So I think that up to now, people or the research community has focused on one type or the other, but we need to compare both of them. And finally, we wanted to say that all this has been published. This is part of the PhD by Juanjo. So we have a journal article, another article at the SIF. Everything is open access, so you can get information from there. And I would like to finish by thanking the Council of Valencia, the contractor, ICED, Ingeniería de Estructuras. Those are the people who did all the structural analysis at ambient temperature and designed the operation for changing the elastometric bearings, the supports. And finally, Carlsen's, who is the monitoring company who did all the monitoring of all the operations. And that's all. Thank you so much for the opportunity.